first, thank you, Garrett, for giving us the opportunity to give this presentation. Yeah, secondly, I want to thank everyone who is attending to give us the time to present, that we can present this to you. So Ernst and I will give this presentation. Let me see. So first, we will introduce ourselves to you. Secondly, we will talk about the company we're working. It's Krone in Dordrecht. After that, we will start talking about the project we've been working on for the last years. It's a multi-phase flow meter. After that, we will go to the architecture and the block diagram of the flow meter, and then we will talk about having MATLAB as a programming language. And in the end, we will have an opportunity for question and answers. But if in the meantime someone of you has some urgent questions, please don't hesitate to ask them to Jorik, who is moderating this for us. So first, I want to introduce myself. So I'm Ralf Olieslagers. I'm an embedded software engineer. I graduated from the Hogeschool West-Brabant in 1999 in electrical engineering. I'm married with Ilse, and we have a son of 6 years old. So in the meantime, it's almost more than 20 years, I worked on the following projects. I started with programming electric scooters, sealing machines, ear, nose and throat, doctor instrument control panels, PLC field bus communication devices. Also worked intercom systems between vehicles. Also as a contractor, I also worked working in climate control systems for greenhouses. Also saw someone attending from that company in the invitation. So yeah, if you're listening, send my regards to Arno, which was my colleague then. After that project, I worked at heating control systems for residential heating. So central heating equipment you have all in your home. And 5 years ago, I started working at Krone, where we make industrial flow meters. Okay, so that's my introduction, and then yeah, perhaps
let's see if that's working. Okay, shift F5. Yes, okay. Can anybody hear me?
Yeah.
Okay, well, I'm Ernst van der Pols, 55 years old, graduated in electrical engineering some 30 years ago already from Delft Technical University. Telecommunications direction, but most of the work I did was in control systems for power electronics, as you can see from 1990 with Holik in Ridderkerk. Power electronics for drive systems, for industrial cranes, for railways, and all other kind of electrical moving stuff like trucks and also naval vessels. Good to see that was already in the previous century that was worked on in the Netherlands. Perhaps a bit premature in some ways, but today it's all gearing up. Before joining Holik, I worked a couple of months with Automator in Sliert, which is actually the same company I'm working now, Krone in Dordrecht, which is Krone Automator. So there are some colleagues here that are now leaving for retirement, and I met in those days. After Holik, I worked with Technolution on a few projects. DFP Laboratories. This is a thing to notice because I worked there on a tool to generate code from UML and C, and we generated C code from it. So that's my main interest also in the code generation part of MATLAB and similar tools. I also worked with television, which is a thing that, well, keeps you famous on the street. The first years of The Voice of Holland, I was involved in making the chairs go around. That's why you can see me sitting in there as well. After that, I worked again on power electronic systems, power converters for railways and high voltage equipment, smart grid protocols and stuff like that with Inter and later on DINIC. And since a couple of years with Krone, more or less again, now Krone New Technologies, development of flow meters. To give an indication, I'm not that a fluent MATLAB user actually. Already familiar with it from early days on and with HOLEC. But then I had my colleague who presented in one of the previous sessions, Han Geerlis. This is a really fluent MATLAB user, so there was little use for me to put in at hand as well. But I used it with Inter recently as well, MATLAB Simulink, also for code generation, for power control, and of course now with Krone in the flow meter that we are presenting. So Automator was in Utrecht, they moved to Dordrecht, and Ralph will take over to give you an introduction on this site here. Yeah.
Oops. I'll see my screen then. Yeah.
Yep, that is.
That was the introduction.
I think you're on mute again, Ralph. There's a technical glitch there. There we go. Still on mute. Still on mute. There you go. Okay, you're good now. Okay.
Okay, sorry for the glitch. So Ernst and I are working in Krone in Dordrecht. It consists of an area of 70,000 square meter. It was previously a Philips factory, Dordtse Metaalindustrie Johan de Witt. They produced electric motors in this site. For instance, the motors of the Video 2000 system. If you see, like from Version Bay, which is in the Eindhoven region, it's about 80 kilometers to Dordrecht. So the region of Rotterdam doesn't host any of the big tech companies like ASML or Philips or NXP, but there are in fact quite a lot of instrumentation producers and developers in this region, of which one Krone is one of them. So yeah, don't think that only the Eindhoven region in the Netherlands hosts IT or high-tech companies. It's also in the Rotterdam region quite some interesting companies. So now we are like 50 years later. It's now part of the Krone group. So here you see the main site. The old Philips buildings are now used as our production facility, where we produce our equipment. This is the part where R&D is located. We also have like a warehouse, and here is the building where the Philips motors were located, were produced. So as I told, Krone Dordrecht is part of the Krone group. It's located in Duisburg in Germany. Our R&D locations in Duisburg, Dordrecht, in Romans-sur-Isère in France, and in Wellingborough in England. And besides that, there are also in 40 countries around the world, there are production and sales locations. So it's quite an interesting company to work at. So what do we produce? So in Krone Dordrecht, we develop and produce electromagnetic and ultrasonic flow meters. They're used for a single phase flow measurement. And what do we mean then with single phase? Is that it's like through the flow meter, you can only measure only a liquid or only gas at one time. And what kind of media do we measure the flow of? It's like oil and gas, water, chemicals, food and beverage, like a cola, liquid chocolate, or beer, which is my favorite to test one of those when a flow meter is tested with that liquid. And we produce them in like very different sizes, so small, medium, large, from DN6 to DN3000, which is like a diameter of 6 millimeters to about 3 meters. And they're used in like the following industries, so directly at oil wells, oil refineries, in gas stations you find flow meters of Krone, bunkering of ships, so the ship also has to go to a gas station, but with the ship mostly the gas station visits the ship and not the other way around. Their meters from Krone are used. They're used to measure natural gas, biogas, helium, in the chemical industry, in the food industry, water distribution, and wastewater treatment. Okay, so if we now, if you produce a flow meter, you also want to calibrate it. Like with, in a small flow meter, it's quite simple. You just pump a certain amount of liquid or air through it, and afterwards you look if the number which is on the screen says the amount of liquid that you pumped through it, and then it's okay. So how do you do that now with a big flow meter? It's like here, like one of the bigger ones, or here also quite big. You just have like a really big amount of water which needs to be pumped through the meter. And here you see, like in our production facility, there's like a really big pipe, and there it goes here to the roof. Here you have then like a really big calibration tower, which is 44 meters high, which can contain 500,000 liters of water. And there, once you want to calibrate a big flow meter, you just open the valve. You know how much water is inside the tower. You'll go through the flow meter, through the roof and through the flow meter. It's being kept there. And then at the end, you can also calibrate the really big flow meters. Yeah. So that concludes the introduction of Krone in Dordrecht. I don't know if there are already some questions or everything is clear.
So there's maybe one question, Ralph.
Yep.
So what makes these things hard to make? So is there a lot of maths inside there? Is there a lot of embedded systems? Is it simple? What makes it so difficult?
So if you go here to the existing flow meters, it's like there's like embedded electronics inside this enclosure, and the main feature of the flow meters is that they don't cause any resistance through the flow which goes through it. So if you have like the water meter you have at your home, there's like a small turbine or propeller inside which measures the water flow. Yeah, we can't have that in industrial flow meters, because that causes, it's a mechanical part, and it causes too much resistance in measuring the flow, and yeah, that will limit the amount of liquid or gas you can pump through it. So that's why there cannot be any obstruction inside the pipe. It just needs to be a straight pipe. And being said that, there's like all the equipment to measure the flow has to be put around the pipe. So there's like a big coil put around it, from where you introduce like an electromagnetic flow, electromagnetic field to measure the flow speed. So, does that answer your question, Garrett?
Yeah, thank you. Thank you.
Okay, yeah. Okay. And the project that Ernst and I have been working on for the last couple of years. And first thing to tell is that we are not the only two people who worked on this meter. It's like in the end of the presentation, I will show like that there are like more than 50 people who worked on making this product. But yeah, we are now the two guys presenting this to you. Okay, it's like a multi-phase flow meter. So which means it can be connected directly to an oil well. You can see right here, it's like next to a pump jack. And yeah, with a flexible hose, you can connect directly the oil mixture which comes from the oil well to the meter. And what makes this flow meter now so special? It can measure the amount of gas, oil, and water inside what is pumped through it immediately without separating those three phases. And yeah, that's why it's called a multi-phase flow meter. So it's like it can measure the gas phase, the oil phase, and the water phase independently, yeah, without separation. To give an idea, this device is like 3.5 meters long. It weighs about 1,200 kilos, which is like stainless steel, magnets, and aluminum. And it contains more than 1,000 stacked permanent magnets. Now, why do we need those magnets? In this meter, there's like a principle which is called magnetic resonance is been taking place, which is comparable with what they use like in medical imaging in an MRI scanner. But we use the magnetic resonance to calculate the flow speed which goes through the meter, which we will show in a short video after this slide. But yeah, to complete this slide is that here in this part is like all the electronics is located. It's like here we have like the low voltage box where all the embedded low power electronics is placed, and on the right we have the high voltage box where the high power electronics is being stored. And also with this flow meter, there's like totally no obstructions inside the pipe, so there's no resistance added to when we pump the oil mixture through the meter. Okay, so now I'm going to try to show the.
There we go.
The M-Phase 5000 is a multi-phase flow meter for the simultaneous measurement of oil, gas, and water, and is based on the principle of magnetic resonance. It has been specifically designed for the upstream oil and gas industry. The large dynamic flow range of the M-Phase 5000 ensures a useful application during the whole life cycle of an oil well. Magnetic resonance makes use of the fact that oil, water, and gas contain hydrogen atoms. These hydrogen atoms possess a small magnetic moment, which makes it possible to count them. For this purpose, the fluids are exposed to a magnetic field, which causes the hydrogen atoms to align to the applied field. Subsequently, the hydrogen atoms are excited by radio frequency pulses. Hydrogen atoms respond to the pulses and send back echoes, which are recorded. The amplitude of the echoes and the rate at which they decay is used to calculate the flow rates. The difference in magnetic resonance properties allows making a distinction between the flow rates of oil and water. Hydrogen atoms in oil align faster to the magnetic field than hydrogen atoms in water. When applying a short magnet length, the measured signal will be dominated by the oil. When applying a longer magnet length, both oil and water will contribute to the measured signal. By comparing the signals in these two situations, the oil and water fractions can be determined. Additional information on the gas velocity is obtained by exciting a gradient coil. The coil induces a magnetic field, which is strong in the top of the pipe and weaker at the bottom. Tuning the frequency of the radio frequency pulses to the magnetic field strength allows performing measurements in selected slices in the pipe. From this information, the gas flow rate can be determined. The M-Phase 5000 is a revolutionary flow measurement solution for multi-phase flows and enables optimizing oil and gas production. Besides enhancing the management of the reservoir, there are more benefits to consider. Single measurement principle, resulting in a transparent flow rate measurement. No radioactive source needed. Fully automated inline fluid characterization removes the need of sample handling and yields fluid properties at actual conditions. Full bore design. Pressure drop and wear are reduced to a minimum. Large dynamic flow range up to 1/60 allows measurement of oil wells during their full life cycle. Accurate flow measurement, up to 100% water to liquid ratio. Liquid measurement insensitive to sand, scale, wax and fouling. Find out more at www.kron.com.
Okay, so I'm trying to switch back to the presentation. Is this visible?
Yes.
Okay. Yeah, so to summarize, the meter can measure like oil, water and gas simultaneously. And it's used to detect when oil wells are producing too less amount of oil. Because at a certain, when they produce too much water, it costs more to clean the water than what the oil company will get in return for the produced oil. Okay, so when developing the device, besides the whole magnetic resonance principle, which I am not an expert in, but which my colleagues have worked on, there were some challenges. So like the main challenge was like the user interface. As you can see, this device totally has no display or LEDs or gauge present on the device. So it's only like a Modbus or Ethernet connection present. The device also needs to operate with a high operating temperature range from -40 to +80 degrees. It's also like it needs to withstand a high pressure of up to 100 bars. And it cannot cause an explosion, mainly because the meter is used close to an oil well, and that can be like that. There's like an explosion-safe environment there. Okay, that summarizes what the meter is doing. So now I want to tell something about the architecture or the block diagram of the device. So here you see the flow meter, and here a schematic version of the electronics. The embedded electronics will produce like the magnetic resonance pulses needed to calculate the flow rates. They are amplified in the high voltage box, then tuned to the medium and sent to the radio frequency coil, and that will produce data which is then being captured by the high voltage box electronics again and sent back to the embedded electronics. And from there we can calculate the flow rates of the oil, water and gas independently. At first, when this project started, we developed the flow meter traditionally, so with the waterfall model. So first the mechanics, then the electronics, then the firmware, then the software, and then calculate the flow speeds. It was without MATLAB, and also the embedded PC, what you see here, was not present at that moment. And that means that when we made the software, that when we wanted to make adjustments, the whole development process needed to start over. The electronics needed to be changed, the firmware needed to be adapted, and that was not flexible enough, and it cost too much time to develop this device. So at one moment we said, okay, we want to really use this device as a research tool, and we want to, from a PC, want to control the flow meter via MATLAB. So we then approached MathWorks to ask for the multi-phase flow meter toolbox. Yeah, you see that it's not available because of the wink. So yeah, that's why we developed the multi-phase flow meter toolbox ourselves. So with a PC, we can connect via Ethernet to the device and then control the whole flow meter via MATLAB. So we send the pulses via the PC to the electronics, to the device. The data is being captured, being sent back to the PC, and there in MATLAB there are all kinds of flow calculations done with all the tools available in MATLAB. And once we have then a stable version of the flow calculation, we convert this flow algorithm into an embedded application with the MATLAB coder, which converts the MATLAB code to C++, and that runs then on the embedded PC. And that concludes my part of the presentation.
So Ralph, maybe just before you go away, so if I understood correctly, you said a couple of things. So when you first started, you didn't use MATLAB and you found it very difficult to kind of change and iterate. So then you moved towards wanting to control and have quicker design experiments. So you started off by controlling your setup, and then you evolved to generating C++ code for some of the embedded devices. So I think that's a very interesting thing, and I think Ernst is going to tell us a little bit more about that. But before we do so, there's a question from Sanjay, who was very impressed by the video, so I'm glad we went through that. But he asked the question, what is the typical settling time for such measurements?
The typical, sorry?
Settling time.
Settling time.
So you mean the update rate, or?
Yeah.
Yes.
I guess so.
So when the device is up and running, it will produce one sample per minute roundabout.
Very good. So 1 sample per minute. Did you say 1 sample per minute?
Correct. Yeah.
Yep.
Okay. Very good. And then maybe just one last question before we go to Ernst. What kind of accuracy do you get? Is it like super duper accurate? Are there errors? Does it accumulate over time? When we pump our petrol in the cars, is it because of Chrome is super accurate, or are we getting ripped off because there's little errors accumulating over time, and what we should be doing is putting petrol in our cars in the morning?
So the closer you get to the when paying for an amount of fuel, the more accurate the device needs to be. So this device is really close to an oil well, and it's more designed to detect if there is like still enough oil being pumped up at that oil well. So at that moment, it's not really critical that the accuracy needed to be at 0.0001% accurate. It's more like you need to make sure that there is not being pumped up too much water from that well. So that's like the main. If you really want to measure high accuracy, we have like a different type of flow meter. It's like a custody transfer flow meter, and that's really calibrated to give the high accuracy, and also for oil. And this meter is also really accurate, but it's not the main purpose of this flow meter to be high accurate. It's more the main purpose is to detect the different amount of oil and water inside the mixture.
Right, and maybe just one last question that came from Ronald. How much does this device cost? Ballpark figure?
So that I don't know Exactly, and they're not available on eBay, of course, but yeah, you can imagine like that 1200 kilos device, with quite high-end electronics in it. It's not a couple of €100 that this device costs.
Yeah. Very good. So maybe Ronald's asking a bit more about it. Maybe in the Meebo you guys can talk about that, and in the meantime you can figure that out, Ralph. So Ernst, do you want to kind of continue with your presentation to talk a little bit about where MATLAB was used and go into a bit more details there?
Yeah, I'll share my screen. Let's see. I have to select screen. And then continue there. Just a bit of a. So let's see. 5. Okay.
Yes, we see your screen.
Yeah. Now I joined only a couple of years after they already had started creating a lot of MATLAB code, and first not directly for the MATLAB part, but at some point I took that over from other colleague. When I joined the project, I realized that there was a connection with my graduation paper, which was about actually telecommunication software, but I looked then into development models, making the development of telecommunication software or software systems in general more easy and more quicker. And from literature, I had made 4 categories of development models, which I have depicted here. Like at first, of course, the traditional waterfall model, nowadays known as the V model. The 4th category was the what I was calling it the version model, like rapid prototyping, things like that. So you do things iteratively. The 3rd was what I called operational model, which means that you have your requirements or your specification of your system written in a formal language so that you can operate it, you can execute it already in early stage, and perhaps if possible also implement it or implement it automatically, or even the design automatically into your system. And the 4th category was, well, at that time, quite mysterious. You had expert systems, things like that. And the Star Trek replicator, I call it the knowledge model approach, that you create your system based on all kind of knowledge that you have collected in a system. Now I realized with the flow meter that was working on here, that each of these models were actually used in this project. The waterfall, or actually V model, for the physical creation of the device for the customers. For the project team worked on a Scrum basis with sprints every, what we had, 2 weeks, 2 sprints at that time. Gradually improving the functionality of the flow meter with different kind of oil wells and things like that. But of course, the interesting part, which is this presentation about the automatic code generation, the operational model based on MATLAB language and with automatic code generation. And in the end, well, one of our physics colleagues also looked into using machine learning to see if we can derive the characteristics of the oil and oil flow automatically based on large data sets. So nowadays, with also 3D printing, which we also have here in our laboratory at Kronen, you can see that what was 30 years ago just ideas and only in literature available, actually all these methods are now in place in the industry. Although I should say that there's still a lot to work on, because when I look at other projects running here, MATLAB and MATLAB is used, but code generation, stuff like that, and machine learning, it's all kind of immature yet and have to grow. Now I'll continue with this, the knowledge model, operational development. Of course, I hope you all know it with MATLAB and MATLAB Simulink, perhaps. I also, with my previous job at Imtech, used MATLAB Simulink for building models and generating code. But just doing it with only MATLAB was a bit new for me. And of course, it can be done. We do not use here the embedded coder, just the normal coder. The generated code runs on embedded PC, so that works fine. MATLAB is, of course, used throughout the whole development process, especially, and I think mostly by our physicists, as I've shown a bit more here. They have the measurement data to analyze and to develop the algorithms for it, and the models to for each kind of well, it's thick oil or more fluid oil, to have a suitable model to calculate the flow from the measurement signals from the meter. And that's not only the part. We have user interface to control the meter from the PC, from MATLAB, for our physicists and developers. There are also user interface for the calibration of the meter, and each meter before it's shipped, of course, has to be calibrated and has undergone some tests at production. We also use MATLAB for that. And then there's, of course, the embedded code part, which I was more or less responsible for. So I had to make sure that the algorithms ended up correctly in the embedded software. So for that, my colleagues were already using that, but I extended it the possibilities of the unit test framework in MATLAB. As you can see, we have a lot of tests running. Also tests that use the meter. So from running the test in MATLAB, we can connect to the meter, to the embedded electronics part, and we can run tests from unit tests from MATLAB with using parts of the meter. And then, of course, there's a step to the coder. So if you say, okay, this all looks fine, I can run the coder and lean back. Well, that is what I was hoping to do, because the physicists, of course, have created all these great algorithms already perfectly. They work. They say, okay, this works fine, so it should work equally fine on the meter. You can see here my colleague Ralph in the laboratory with the flow meter in the test setup. Problem is that MATLAB is, of course, as you know, a dynamically typed language with the type, which is great if you are doing your simulations and do quick things, and everything is a double, so you don't have to mess around with 16-bit shorts or whatever. But if you are going to generate code in a strong type language, you have some way to translate it into this language, in our case C++ or C++. And of course the coder is doing the bulk of the job. But unfortunately the coder has to figure out what kind of types there are, and it does so by going through all the code and looking through all execution paths to see, to figure out what kind of types are used. And that might give some problems. Of course, there are things that are not supported by the coder. So, okay, you can have that list of functions that are banned from the parts of the MATLAB source that have to be go through the coder. But there still are issues that may get passed unnoticed. Like I've indicated here, this simple example of some log data copied from the internals to some kind of log, and it runs all fine. Coder is happy with it. Code is produced, but when it's running in real time, there might be a situation that something is not found here, so the result might be none, and then the coder hits an exception because the generated code did not take that into account. So those are issues that I and my colleagues, also the physicists that create this code, should be aware of and prevent. So the question is, how can we use this language? At one point for simulation, you can do all things you like, but the parts that are aimed for code generation should be restricted to go through the coder without any problems, and also when running embedded should give no problems. Now to solve that and to help prevent problems, we created several functions that hide the implementation issues. I have a simple example here. When you need strings, or strings is a new item anyway in MATLAB. So you had the character arrays, but now you also have real strings. It's somewhere in coder support, but if you want to have dynamic string, well, strings of different sizes, then you really have an issue. So created a function, helper function, that you can use to initialize at construction an empty string, and it will go through the coder and also will support having different sizes of strings. This is just an example. Similar functions you can make for other issues that you typically run into in your application. Now that is of course fine, we can look into all these issues ourselves, but it would be nicer if the language also would support preventing these kind of things. And then we can look at other languages which are kind of similar. Let's say there are scripting languages, weak typed or dynamically typed, but also are used more and more in real programs, and for that are longing for stricter types. And I have two examples here. The PowerShell, for example, you can use it as a scripting language, just a function with an argument with no type. It will accept any type here, a floating point or fixed point, and it produces something. If you put a string in it, well, it will give a strange result, perhaps. You can see it dynamically. But if you say, no, I want to make sure it has an unsigned integer, you can also specify the type. And if you put a floating point argument in it, it will give an error. Same with PHP, known for websites and things like that. They also moved from untyped arguments to a notation that you can specify. I'm sorry, I jumped out. Yeah, there I am again. Sorry about that. They specified the. You can specify the type, and then it will also check that type. Now, is that possible with MATLAB? Was my question. I looked around for it. Well, there's you can, for example, use asserts. The coder accepts asserts, and it will handle them. And that way, you can at least write code that the user knows. Okay, the argument has to be an unsigned integer. But since I think the release 2019b, you also have the arguments validation possibility, where you can specify the argument size, dimensions, and also the type, and all other kinds of things. So that way, the coder could know what kind of type is to be used. Unfortunately, it is not supported by the coder yet. Coder lags behind a bit, so I'm looking for the guys at MATLAB to work on that and to add things like that to the MATLAB coder, so that we can come with a MATLAB that's MATLAB language that can be used both for the simulation with a weak typed system, but also for the parts that we want to generate code from with a more strong typed language. Until then, and perhaps even after that, we still need manual intervention to guide our physicists in what they should do or cannot do for creating the embedded code. I think, yes, that was my part of the presentation.
So Ernst, thank you very much. So I know we're slightly over time, but I think there's a few interesting questions that have come through, but maybe just to call them out. So somebody asked, are you using continuous integration system when you're running your unit tests? So you had a little chart there where you're showing your unit tests in MATLAB. So are you using a CI system? If yes, can you share which one you are using? That was one question. And then the other question that kind of came through is, are you using the same unit tests for the generated code?
Yeah, we're using continuous integration with Jenkins. Actually, the code is just the generated code is a part of a bit larger system which runs on the embedded PC, and that is compiled on the machine with in a Jenkins environment. And in that we also run the unit tests. So that's yeah, it's part of the integration, but it depends. Actually, the parts with using the hardware is not part of that, because that's pretty difficult to arrange. It could be arranged, but you need to have a setup that's active, and we cannot have active measurement sets all around, of course.